All right, so now that we've reviewed vocabulary regarding waves and how to calculate specific parts of a wave, we are in this video going to talk about a specific type of wave, and that is sound waves. So our topic for today is sound. Our objective is to be able to describe a sound wave and identify various characteristics of a sound wave. Your all's essential question that you all should answer in about a 1 to 2 sentence summary after watching this video and taking notes is, what is a sound wave and how fast does it travel? So let's go ahead and zoom in on what a sound wave is. Let's start from there. So a sound wave is a mechanical wave. So remember when we talk about the difference between mechanical and electromagnetic waves. Mechanical waves must have a medium to travel through. Remember, medium is basically a substance, must be traveling through a substance. So if we think about it, sound waves can travel through air, that's a substance. They can travel through water, they can travel through solids, right? You can hear people talking through walls sometimes. They're thin walls, but they cannot travel in a vacuum, which makes them a mechanical wave. They cannot travel in, sound waves cannot travel in space, all right? The motion of a sound wave is longitudinal, all right? So it is a longitudinal wave as well, which means that the particles are moving parallel to the wave's direction. So if the wave is moving to the right, our particles are oscillating, all right? Remember that word, oscillate. Which is movement back and forth. Those particles are oscillating back and forth parallel to the direction of the wave's motion. All right, so that's kind of the basics on what a sound wave is. All right, so now we'll go into how fast the speed of sound is. All right, so sound is pretty fast. It moves generally at 346 meters per second at standard room temperature, so somewhere around 25 degrees Celsius. So 346 meters per second is pretty fast, right? But sound speed is going to be affected by things such as temperature and density of whatever medium or substance it's traveling through. So we'll look at how these are affected or how these things affect the speed of sound. So temperature is affecting sound because temperature is directly correlated to the amount of kinetic energy that air particles or whatever particles of that medium have. So the more kinetic energy these particles have, meaning it's a higher temperature, the faster the sound can travel. So if you think about how sound is moving, it's the oscillation of these little particles back and forth. So if they have more kinetic energy, it means they're oscillating more and faster. So that allows sound to travel faster at higher temperatures. Density is very similar. It has to do with the kinetic energy of the particles as well, and of that medium that sound is traveling through. However, density is describing how many particles are in, or how dense that medium is. And sound does travel faster in less dense mediums, right? So if you look at the difference between a liquid and a gas, right, sound is typically going to travel faster in air than it does in water. And the reason for that is because these particles and gas particles are less dense and they have more kind of just room to move around. So they have more kinetic energy because they have more room to oscillate. All right. So density is something that also affects sound as well. The sound travels faster in less dense mediums. So just a great example of that is just think of if you've ever tried to talk to your friends, in the air, above water, and then underwater, that sound travels a lot slower in the water, in a liquid, which is a more dense medium. So then we can get into some really cool, unique characteristics of sound waves. So the first vocabulary term and characteristic of a sound wave is something called resonance. Now, all waves can develop this resonance. However, something really, really cool happens with sound waves when they are in resonance with another object. So when an object vibrates, resonance is defined as when an object vibrates at the same natural frequency as another object, it forces that object into motion. So I know that you might have heard of this myth that if you are an opera singer and you can sing at the right pitch, it will actually shatter a glass. And that actually is true. And that is because of resonance. So if you have one object, I meant to put this in highlighter mode, all right? One object with a certain frequency, and you can get this frequency to match the natural frequency of the second object, this is called resonance. And it's going to force that second object here into motion. So if you are forcing a glass, literally made out of glass, into motion, it's going to become highly unstable and shatter. So this is a really cool phenomenon that happens with sound waves in particular, is that you can, at the right pitch or at the right frequency, remember pitch, and I will put this just so you all can see this. Remember pitch, and I'm spelling that wrong. The pitch of a sound is determined by the sound wave's frequency. So at the right frequency or pitch for one object, you can actually force another object into motion as long as it matches that other object's natural frequency. Another cool thing that happens with sound waves in particular is something called the Doppler effect. Now, the Doppler effect you all might be familiar with already, even if you couldn't put a name to it. And that is when the relative frequency of a moving sound source changes depending on its distance from another object. So I always like to use the example of an ambulance. If you all have ever stood somewhat far away from an ambulance and it sounds really low in pitch and very just kind of a lower frequency, right? You can, as it's far away, it sounds very different from when it is closer to you, right? And that is because of the Doppler effect. That lower pitch from the lower frequency is because of the distance between two objects. And that moving object, as it gets closer, is going to appear to have a higher frequency and a higher pitch. So if y'all are interested in this, and definitely I would look up the video of an ambulance, driving closer to a stationary object, and you'll actually hear that difference in pitch of an ambulance as it gets closer and closer to you. As you're standing there, you start to hear it get higher and higher in pitch as it moves forward. Now, the actual frequency, I do want to point this out, the actual frequency of the ambulance, of the sound that the ambulance is putting off, is the same. It's just to this observer here, and I'll highlight them here, just to this observer, it appears to be changing. So I do want to make this clear that this is a relative frequency, meaning it is from the perspective of this observer. The actual frequency that the ambulance is putting off from its sound is not changing. It's just from this perspective of this person standing here, of this moving object getting closer, putting off this frequency. It appears to be getting higher and higher. Okay. So that is really all we're going over in terms of sound. Now, if you were to want to calculate sound, obviously we would use our wave equation, which is the velocity is equal to wavelength times frequency. But these are just specific vocabulary terms, specific characteristics of sound waves that help us in understanding how this wave travels through our universe. So I hope you found this video interesting. Again, please remember to write your 1 to 2 sentence summary at the bottom of your notes here, and I look forward to discussing this with you all more in class.